this video, we're going to take a look at the strength of bases now. So just like acids, there's strong bases and there's weak bases. A strong base will dissociate 100% in water, so it's to completion, just like the strong acid. We represent it with a one-way arrow. For example, here we have BOHS, and it's dissociating to produce B plus and OH minus. So we have the strong base basically 100% becoming B plus and OH minus. And your strong bases, you should memorize them. They're your hydroxides of group 1 elements, so LiOH, NaOH, KOH, RbOH, CSOH, and also your group 2 hydroxides, COH2, BaOH2, SROH2, but that does not include magnesium hydroxide. That's there by accident. That is not a strong base. That's because the magnesium hydroxide is sparingly soluble. It's not very soluble, so it doesn't become 100% OH in solution. So just an example of a strong base, if we had, let's say, NaOH, that's a strong base, and that goes into water. 100% of it will become Na plus AQ, and then OH minus AQ. That's 100%. All of it becomes the ions and the OH minus there. Now, you could write this as a solubility equilibrium, where this is a solid, you throw it in the water, and then it becomes Na plus and OH minus, but we probably wouldn't put the double arrow here because it's a strong base. So if you write it as a solubility equilibrium, you do have to remember that it is a strong base, and if we're talking about it in terms of strong base, we're just going to put a one-way arrow there. Okay, so if you're saying strong base and you're showing dissociation based on strong base, just put that one-way arrow to show that it's 100% dissociation happening for strong bases specifically. Now, weak bases are a bit different. Many of your weak bases actually don't have OH directly in the formula. Now some do, like magnesium hydroxide or any of the other hydroxides that are not part of this process here. So some do have it in there, but many of them don't. Weak bases partially dissociate with water to make hydroxide ions, and so the equilibrium is more so to the left, and very few of the, I shouldn't say acid particles, the base particles are going to ionize or dissociate. Let's just fix that error there. For bases, we say dissociate. And it is a reversible process. You'll notice that a lot of the weak bases that you're going to see are amines. So amines are weak bases. Ammonia is a weak base, and there are other OH bases that are not listed as strong that are considered weak bases as well. And so here's an example of a weak base situation. We have the weak base B plus H2O. Since it's a weak base, B is going to take H from H2O. That's going to produce BH plus and then OH minus, and we're going to have a double arrow there to show that it's a equilibrium and that it's a weak base. We'll do another example. Let's choose methylamine. So methylamine over here is CH3NH2. That's our weak base. We know that because it's an amine. We're going to write it as aqueous. We're going to make it react with water. So weak bases will often do this reaction with water here, which is liquid. We're going to do our double arrow. Since it's a base, it's going to take H from water, and it's going to become CH3NH3 plus, because it gained an H, AQ, plus OH minus AQ. And so that's a weak base dissociating. It's not 100%, it's an equilibrium, and the equilibrium is more towards the left side, so you don't get a lot of OH being made, which is why it's called a weak base. Just like we saw for acids, weak acids, you can have a Kb. And so the Kb is your base ionization constant. And essentially you can make Kb by doing it the same way you would do for a Ka. So you would write out your reaction with the weak base first. So let's say this is your weak base, BAQ plus H2O, liquid, double arrow, BH plus AQ plus OH minus AQ. Your KB would be your concentration of BH plus times your OH minus over your concentration of B. So essentially your conjugate acid over your base, and then that conjugate acid is multiplied by the hydroxide ion. And that's how you would write a KB expression for a weak base. You can take a look at the KB table to see examples of weak bases as well. So if we go back to our table here, you'll see a lot of the weak bases are some amine-like compounds, and you can see the KBs over here. And you can also see, so if this is the base, we assume that the base will gain a hydrogen, one hydrogen ion, as opposed to several. So this will gain one and become NH2 plus. This will become NH3 plus. This one becomes NH3 plus as well. So they gain their hydrogen ions and become positive. And these are the KB values you can see here. And of course, the smaller the KB, the weaker the base. The higher the KB, the stronger the base is. So we'll do an example here. We're going to write a KB expression for methanamine. So methanamine is CH3 NH2. You can go to your KB table here, find methanamine, CH3 NH2. You can also remember it from organic chemistry. Because it is a weak base, since it's an amine, we're going to make it react with water, a liquid. We're going to do our double arrow. It's a base, so it's going to receive an H, and it's the N part that receives the H, so we're going to have NH3 plus AQ. That's our conjugate acid now. And then we're going to have some OH minus AQ. And now that we have this written out, and it's balanced, because we're just doing a proton transfer, we're going to write KB is equal to the conjugate acid, CH3 NH3 plus, times the hydroxide ion over the weak base itself. But keep in mind, you would not put water in there because water is a liquid, and there's no such thing as that concentration for the water there. So there we have it. That is a weak base KB. So we saw the difference between strong bases and weak bases, with strong bases dissociating 100% and weak bases not doing that 100% and existing more so as an equilibrium. And then we saw that for weak bases, because they exist in that equilibrium, in that reversible reaction, you can write a KB expression. You should memorize your strong bases and then know that your weak bases are essentially amines, and the amine portion receives the H+.